Alaikum. This is lecture number 7, Physics 281. I will discuss the inductance coupling between two oscillators. The first oscillator consists of a capacitor and inductance. The current through this is I1, and the second consists of a capacitor and inductance, and the current through the second circuit is I2. The equation of motion of the first circuit is given by the potential across the capacitor Q1 over C1 plus the potential across the inductor L1 dI1 by dt plus the potential or the electromotive force due to the variation of the magnetic flux coming from circuit 2 on circuit 1, which is M dI2 by dt. This is equal to 0. M is the mutual inductance. This is a magnetic coupling. Now, for the second circuit or the right circuit, we have the potential cross the capacitor Q2 over C2 plus the potential across the inductor plus the mutual inductance, which is MDI plus the potential due to the mutual inductance, which is MDI1 by dt. Now, to solve these two equations, assume I1 is A times e to I omega t and I2 equal B times e to I omega t. We have to solve these two equations for omega now. In this case, Q1 is minus I over omega I1, I1 dot is I omega I1, Q2 is minus I over omega I2, and I2 dot is I omega I2. Now insert these in equation 1 and 2. We get these two equations, 1 and 2. Now multiply from left by omega over I L1 for the first equation, and for the second multiply by omega over I L2. We reach these two equations. Let's define omega 1 square is 1 over L1 C1 and omega 2 square is 1 over L2 C2. Now we get these two equations, rearrange and divide equation 1 by 2. We get this expression. Now this expression can be written in this form. Let's define what's called the coefficient of coupling K, which is M over square root L1 times L2. In this case, this equation can be written as omega 1 square minus omega square times omega 2 square minus omega square, which is K square omega to the power 4. Now solving this equation for omega gives the frequencies at which energy exchange between the two oscillators. Now a special case is omega 1 equal omega 2 equal omega 0. That's L1 equal L2 and C1 equal C2. In this case, we have two modes. Well, the first one is omega 0 over square root 1 plus k, and the second one is omega 0 over square root 1 minus k. Now let's move to the coupled oscillations of a loaded string. The loaded string consists of n particles with fixed ends. This is particle 1, 2, and assume that the separation between the particles is constant, equal A, and this we set this in motion, assuming that the tension also is constant through this string. Now let's find the equation of motion of the earth particle. If you look here, this is the displacement of the earth particle from the equilibrium, and this is the displacement of the right particle, which is r1 plus 1, and this is for the left particle, which has a displacement yr minus 1. We did this problem at the beginning of the course. Now sine theta 1 from the figure is given by this expression, and sine theta 2 is given by this expression, and this is for small oscillations. Now the restoring force, the vertical restoring force, is T sine theta 1 plus T sine theta 2. So this is the restoring force. According to these relations, it reduces to this form, minus T over A, minus, because it's a restoring force, Y sub R minus YR minus 1 minus Y sub R plus Y sub R minus Y sub R plus 1 arrange, we get this expression, but this is equal according to Newton's second law m d2y sub r over dt square. Now this is the equation of motion we want to solve for to find the displacement and the modes of particle number r, or the rth particle. Assume again the solution has this form: a sub r some amplitude e to I omega t, then substitute for y double dot and for yr minus 1, yr plus 1. We get this expression. Rearrange, we get finally this expressions. We call this is the fundamental equation. Let's apply this equation as if we have one mass. That's r is equal 1 because the ends of the string is fixed. So r0 is 0 and r2 is 0 because we have only one mass. So we left with 2 minus ma omega square over 2 times a1. In this case we have one mode which is equal or isolates with 2t over m by a. We already solved this problem at the beginning of the course. Now let's take two masses, that's r equal 1 and r equal 2 with fixed ends. We get this expression for the first mass minus a0 plus 2. Here put r equal 1, we get minus a0 which is 0 plus 2 times this expression times a1 minus a1 plus 1 is 2. And then for the second mass, we'll put here 2 minus 1 is 1, 2 plus 1 is 3. A3 and A0 are zeros. Now doing so, we get these two equations. Now arrange and divide these two equations, we get this equation that gives us omega. So solving for omega, we get omega 1 square is t over m over a, and omega 2 square is 3t over m times a. We have two modes here, two masses with two frequencies or two modes. Now to find the relation between a1 and a2, the displacement of particle 1 and particle 2, the amplitude of the displacement of particle 1 and particle 2, substitute omega 1, we get this expression. That's a1 equal a2, so both masses move in phase as shown here in this figure. Now for the second frequency or second modes, substitute in any one of these equations. For omega 2 by 3t over ma, we get a1 equal minus a2. That's the two particles are out of phase. If the one is displaced up, the second is displaced down, and so on. In the next lecture, we will talk about the n modes of the whole string. Thank you.